So after having understood the critical role of mass transfer in chemical and process systems engineering, we move ahead and let's see if we can do the classification and the characteristics of mass transfer operation. So how do we classify mass transfer operations? So what is the criteria we are using? Criteria one, we look at phases in conduct. Criteria number two, we look at membrane separation operations. Criteria number three, we look at type of separating agent. So let's look at the first classification there, which is indicated in Fig 1.3 as phases in conduct. So let's start by looking at the gas, which is of no industrial importance. So nothing much we will be talked about that. We also look at the solid, which is of not much industrial importance there. So if we come back to our gas liquid, there the most some of the important operations there is your distillation, your absorption, humidification, dehumidification. We look at the desorption and stripping. Then the second one is our liquid. So liquid extraction, where we are conducting two mixable liquids and making sure that extraction is done. This is enabled due to differences in solubilities. Then you look at the solid fluid, which is further divided into your solid gas, solid liquid. If we look at the solid gas, we're talking about drying, we're talking about gas absorption on a solid surface. An example there is your activated carbon. Then your solid liquid, there you are looking at leaching, mainly employed in the mining sectors there, and also oil extraction. It's also employed there. We look at our crystallization, and the sugar industry comes into play. Then the liquid adsorption, where we've got a solid phase there. Applications where we are using our activated carbon to remove impurities from water there. So a further look at the gas liquid operations. So our distillation there, which is making use of a difference in boiling points, and more appropriately, as you will see later, a relative volatility being employed there. So our crude oil refining, making of our spirits being typical examples. Then absorption, where we are scrubbing off a solid in a gas mixture into a liquid mixture. And an example there is we are removing our SO2 through use of water or amine solutions. Then if we look at desorption there, where we are saying it's the reverse of absorption, where we are saying the solute that dissolved in a liquid is transferred into a gas stream. And a good example there is removing oxygen from water using steam. Then humidification and dehumidification, so transfer of pure liquid into a gas or vice versa. And one example there is our cooling towers, where we are doing the humidification, and our air conditioners there, the dehumidification. So liquid operations, There, where we are saying a solid is transferred from one liquid phase to another based on difference in solubilities. Um, your recover of penicillin from fermentations. The broth is there, separation of aromatics from kerosene. Then solid liquid operations. So this involves a solid material and a fluid. And as already said, our fluid can either be a gas or a liquid. We talk about adsorption, where we have already talked about making use of activated carbon in gas masks and removing colors from our sugar syrup there. Drying is another operation where we are removal of liquid from a solid by vaporizing it into a gas stream. So drying paper, spray, drying milk powder, and the common one where we are drying our clothes on the washing line. Then leaching, where a soluble component is effectively removed from a solid matrix by a liquid solvent. And an easy or good example there, coffee brewing, where we are extracting caffeine and flavor from beans. Then we look at the applications of using cyanide solutions to extract gold. Then crystallization, where we are looking at manufacturing our salt, sugar, or production of our silicon wafers. Then our membranes, reverse osmosis, where we talked about making use of these membranes to separate our water and seawater there. Then gas permeation. Gas permeation is a good example also, based on molecular size. Dialysis also employed there. Type of separating agent. This is critical. So this defines what is added to a system to cause separation. So there's mass separating agent where we are adding a foreign substance to effect the separation. Then we also have the energy where we are adding energy, work or pressure to remove or to create a second phase, then effect separation. And distillation is one important separation process there. Then we also look at the advantage there, where we are saying that the heat is easily removed and does not contaminate the product. So fundamental principles there which govern mass transfer operation being your driving force, which we have already really talked about. The greater the difference, the faster the transfer. Then equilibrium, the net transfer stops when phases reach a thermodynamic equilibrium. Then transport mechanism, molecular diffusion, is governed by fixed law indicated as an equation there. So this is and we also look at convective transfer, where transfer is due to bulky fluid. So basically, the core concept here is Right. So, in conclusion, mass transfer operations are governed by chemical potential gradients, whether through diffusion or convection. The goal is to drive a system towards equilibrium to achieve separation. So, if we look at the design choice, so we are looking at, are we using energy separating agents, where we are saying best for bulky and heat stable mixtures, and the most common is our distillation. Then are we looking at employing mass separating agents? And this is essential for isotopes and heat sensitive products. And these are made use of despite complexity of agent recovery. Then economic viability, its core, whilst technical feasibility can be guaranteed, but economic viability is also important, because the component of trying to make money by employing these techniques. So one extreme one is extreme dilution, renders many mass transfer operations impractical due to high energy to revenue ratio there. So you as an engineer, what's your role? Is to select most efficient phase conduct method, and separating agents to balance the purity, energy consumption, and your costs.